Local convection coefficient in a pipe. In this case, we have a fluid through a pipe and the heat transfer is occurring in between the surface of the pipe and the fluid, and the heat transfer is from the wall through the fluid or from the fluid to the wall if the temperature of the fluid is higher than the temperature of this wall. In either case, it is perpendicular to the surface. The heat transfer flux is defined as h of x, so that's going to be a local coefficient at this x distance, multiplied by Ts minus Tm. For a pipe, we use Tm, which is the mean temperature of the pipe, and not T infinity, which is the free stream velocity for a plate, external flow. Now, from last class, we noticed that for fully developed flow, this ratio of temperature doesn't change with x. So the derivative of this with respect to x is 0. That means that this that is in this green square is not a function of x. It's not a function of x. So this is the temperature of the surface minus the temperature at some distance r divided by the temperature of the surface minus the mean temperature. And so we are at one point x measuring those temperatures. That's not a function of x. Now, we are going to use that fact and derivate this with respect to r. So the derivative of this with respect to r, so everything is constant apart from t of r. So it's equal to minus 1 divided by Ts minus Tm and multiplied by the derivative of this term, the dt dr. Also, because the original one was a function of x, the derivative is not a function of x either. So it doesn't change along the pipe. So, but what happened at the wall? So at the wall, we also have that the fluid is static, velocity is 0, and we have that the heat flux, it is equal to minus k dt dy, and because r is in the opposite direction of y, so the derivative with respect to r is going to be minus the original one, so that becomes positive, and this is equal to the convection. So the convection is f of x multiplied by Ts minus T infinity, and we are assuming the local convection coefficient at that point. So if from this expression we solve by dt dr, so we have that dt dr is equal to h of x divided by k and multiplied by Ts minus T infinity. Now what I want is to take this expression, and replace the definition of dt dr, that expression that is not a function of x. So we have minus 1 divided by Ts minus Tm and multiplied by dt dr. So this is not a function of x, and this is equal, replacing dt dr by that expression on the top, we have minus 1 over Ts minus Tm, and dt dr is h of x divided by k and multiplied by Ts minus T infinity. Now on the right hand side we can simplify this, and we have that the expression on the left is equal to the expression on the right, which is h of x over k, but also we know that this is not a function of x. So this is not a function of x. That means that h of x is equal to a constant if x is bigger than the distance to get fully developed thermally flow. Okay, we can see that in the following plot. So after the fluid is developed thermally, and that should be thermally, H is going to be a constant. So this is H. This is constant. We cannot tell the same thing in the entrance part. So in the entrance part, we can have one of these options, and that's going to be a question for next time. Okay? But from this point onwards, H is going to be constant. So which is very nice because it simplifies the heat transfer analysis. Okay, we are going to have two different situations. One is uniform heat flux, when we have uniform heat flux all along. So this is Q, and Q is constant along X. And the other situation is that we have the temperature constant. So, or Ts equal to a constant along X. So first I'm going to analyze this situation, and next this situation. So what happens when we have uniform Q along X? Well, going back to the definition, we have that Q double prime equal to H. I'm not saying H of X anymore because it's constant, multiplied by Ts minus the mean temperature. Now, if this is constant, means that the derivative of Q double prime with respect to X is equal to 0, and therefore the Ts dx, so I'm derivating to the right hand side, dTs dtx minus dTm dt and dx is going to be equal to 0, and H is a constant, so we can simplify. Okay, minus dTm over dx, everything multiplied by H is equal to 0. In other words, dTs dx equal to dTm dx. So what we found is that the slope of the temperature on the surface is going to be equal to the slope of the temperature on the mean temperature. So if we compare the two along the pipe, so we are going to have, this is X fully developed thermally, and we have the pipe is here. So we have one and the other. So this is the temperature on the surface, and this is the mean temperature, and those are going to be parallel. This is the meaning of dTs dx equal to dTm dx. We can also conclude the following. As the following, d dx, so this derivative of Ts minus T, d Ts minus Tm equal to 0. And if we use, I'm not going to do it in detail, so using this this approximation, well, not this approximation, the fact that the derivative of a fraction is equal to f multiplied by g minus g multiplied by f prime and divided by g squared. So if we use this into that, we can get to the following conclusion. We can conclude that the derivative of the mean temperature with respect to x is going to be equal to the derivative of the temperature with respect to x at any r. So this is the TR. So at any r that's happening. So at any distance from the middle axis of the pipe. So again we have our pipe. This is X fully developed, and we have now Tm and Tr. So that's going to be the mean temperature, and this is going to be Tr. So this is the temperature at some distance from the center of the pipe. So those are going to be parallel as well. And that's only after the flow is fully developed. Now, what happened at when we have constant temperature on the pipe? So constant temperature means that the Ts dx is equal to 0, right? So it's not changing. So this is Ts equal to a constant. And the rate equation, we have Q double prime equal to H multiplied by Ts minus Tm. And remember that this is constant. So the Ts dx is equal to 0. So a fluid parcel in the pipe will increase its temperature as it moves forward. So the mean temperature, it will increase as we move from one region in here to there, to there, to there. It will keep increasing the temperature. So for our fluid, so if I plot, so this is the temperature in the wall. This is X at fully developed flow thermally, and then the temperature, it will increase. It will start the mean temperature, it will start to increase from this point asymptotically to the temperature on the surface. This is the mean temperature. Okay, so these are the two possible situations that we have for conditions on the pipe, either to constant heat flux or constant temperature on the surface.